Right, let's get straight into it. If you're prepping for your Cambridge Biology 9700 exam, mastering the 4.2 surface area to volume ratio calculations, well, it's not just an option. It is absolutely essential for your success. This specific topic pops up in virtually every single exam series. We're talking about how the size of an organism, whether that's a microscopic amoeba or a giant elephant, literally dictates how it survives. But listen, we aren't just going to run through basic math today. We're going to dig into exactly what the examiners are hunting for so you can absolutely lock in those top marks in this explainer.
So picture this. You walk out of your exam hall feeling completely invincible. You totally nailed the calculation, you found the right ratio, you are on top of the world. Only to realize a few weeks later that a tiny, almost invisible oversight just costs you every single mark on a critical calculation question. You pull up your paper, and staring right back at you is a big red 0. Yeah, no thanks. We're going to completely bulletproof you against that feeling today.
So why does this actually happen? Why on earth would a mathematically flawless calculation lose all its marks? It's a massive trap, and students fall for it every single examination series. Today, we're exposing exactly why ordinary textbook revision simply won't save you here. You see, the examiner isn't just testing whether you know how to use a calculator. They are testing your scientific reasoning. They want to know if you actually understand why a cell stops growing at a certain point, or why specific shapes are favored in nature, not just that you can successfully divide two numbers.
Okay, Section 1, Unlocking the Core Principles. This is where we figure out the theoretical architecture the examiners actually test.
To secure those top-tier grade boundaries, we've got to look way past the raw numbers. This is all about shifting your mindset from a math student to a biological investigator. And what's really wild here is what the principal examiner reports explicitly state. They note that candidates who connect their surface area to volume ratio calculations with other areas of the syllabus, basically showing causal relationships, achieve significantly higher scores. You literally have to show how the math controls the biology. Let's think about a tiny mammal, like a mouse. A mouse has a massive surface area relative to its tiny volume, which means it loses heat to the environment incredibly fast. The examiner wants to see you calculate that ratio, maybe a surface area of 6 square centimeters to a volume of 1 cubic centimeter, and then explicitly state, because of this 6-to-1 ratio, the mouse has a high metabolic rate to maintain its body temperature. Connect the dots.
In just a few slides, I'm going to let you in on a specific examiner clue that completely changes how you should format your answer. It's a hidden indicator right there in the prompt. But first, you need a procedural framework that makes that hidden clue completely obvious when you see it.
Which brings us to Section 2, Securing Your Method Marks. Let's look at the exact step-by-step strategy you need. Complex data analysis really shouldn't cause panic. It just requires a structured, step-by-step procedural framework to secure what we call method marks. Honestly, method marks are your absolute best friend. They are points awarded for your process, even if your final answer is slightly off. This standardized sequence you're looking at is your safety net. Step 1, identify the key elements. Is the cell modeled as a perfect cube? Step 2, apply the relevant biological principles. Step 3, execute your analysis with very clear working. Say you have a cube-shaped cell with a side length of 2 micrometers. First, you physically write down the formula. Surface area equals 6 times the side length squared. Plug in the numbers. 6 times 2 squared gives you 24. Then, write the volume formula. Side length cubed. So, 2 cubed is 8. Step 4. Verify your results. Does your ratio of 24 to 8 simplify to 3 to 1? Yep. And finally, Step 5. Present them in the appropriate format. This sequence proves to the examiner that you're processing things systematically.
And here's the beautiful thing about this framework. It is incredibly versatile. Whether you're interpreting complex graphs, extracting relationships from tables, or selecting apparatus for a practical investigation, following this exact sequence proves your analytical depth. Think about that classic agar jelly cube experiment using hydrochloric acid. If you're given a table of different sized agar blocks, you need this framework to extract the relationship between the surface area to volume ratio and the time it takes for the acid to diffuse and turn the indicator colorless. Spotting anomalies in practical data requires the exact same structured thinking as a purely theoretical paper.
Moving on to Section 3, Top 3 Examiner Warnings. We scoured the reports, and examiners are basically begging students to avoid these recurring traps. Let's look at a massive warning straight from the people marking your papers. This quote right here, it's the ultimate alert. Never, ever leave your working out blank. Please do not just do the math in your head or on some scrap piece of paper. Those process marks are your buffer against silly calculator errors. Show the examiner exactly how your brain got from point A to point B. Even if you hit the wrong button at the very end and write down the wrong final number, showing the correct formula and your substituted numbers almost always guarantees you 2 out of 3 marks. It is a literal lifesaver. Specifically, examiners flag these top 3 fatal mistakes every single year. Number 1, using the wrong terminology for the context, like vaguely saying the amount of a substance instead of using the precise biological term volume. Number 2, forgetting to check your units. This is a classic. You might perfectly calculate the surface area, but accidentally leave your answer in centimeters cubed instead of squared. Bam, mark lost. And number 3, giving generic answers that aren't specific to the context in the question. Always double-check that your definitions perfectly match the exact biological scenario you're dealing with. All right, section 4, flawed versus perfect answers. Let's see what this actually looks like on a real exam paper. Just look at the difference here. Notice how the flawed answer on the left just casually drops a final number? The math might technically be right, but it's completely isolated. It just vaguely says the ratio is 2-to-1, so diffusion is fast. Now look at the top band answer on the right. It systematically justifies its conclusion. It explicitly states the calculated surface area to volume ratio of 2-to-1 is lower than the previous cell, therefore the diffusion pathway is longer, meaning the rate of oxygen uptake will be insufficient for aerobic respiration. Do you see that? Precise comparative connectives, step-by-step working, and grounding the final number in rock-solid biological evidence. This side-by-side perfectly illustrates what examiners mean when they ask for higher-order evaluative thinking. Top-scoring candidates do exactly what you see here. They question assumptions, evaluate alternatives, compare approaches, and heavily justify their conclusions. You're not just doing math. You are critically analyzing limitations. Once you start writing like this, you completely transform from a student just regurgitating facts into an actual biologist evaluating real-world data. And trust me, examiners reward that transformation generously. Section 5. Your crucial next step. We need to talk about avoiding the final, ultimate trap. Because honestly, all this perfect mathematical framing is completely useless if you fall for one hidden trap before you even write down a single number. Think about it. Even with a flawless methodology, what invisible force actually dictates the mark scheme and the grade band you fall into before you even pick up your calculator? What decides whether you just need to state a fact or deeply evaluate a whole concept? It's the command words. The exact command words used in the prompt are the hidden key. Words like describe, explain, evaluate, or calculate. Misinterpreting just one of these changes your required answer entirely. If the prompt says calculate, okay, cool, just do the math and show you're working. But if it says explain the calculation, you have to tie those raw numbers directly back to biological functions, like the rate of diffusion or heat retention. We're going to decode exactly what all those command words mean and how examiners uniquely use them in our next mandatory explainer. So make sure to subscribe to our channel, Ace the Exams, at acetheexams_IGCSE to absolutely excel in your Cambridge examinations. And check out the explainer on screen right now to master those command words and secure your grade. Until then, I want to leave you with a thought. As climate change steadily increases global temperatures, how will the surface area to volume ratio of Earth's mammals force them to physically evolve over time? Really think about it, and I'll catch you in the next explainer.